Hello and once again welcome. This is S.S. Tripathy welcoming you to my channel S.St Chemistry. This is Organic Spectroscopy problem video series, video number 5, in which we shall discuss today two conjoint problems from the great master book Silverstein, Webster and Kiemle, 4.4a and c. So the first problem involving mass, IR, proton NMR, C13 NMR, as well as DEPT, DEPT experimental data, we shall be discussing how to solve a problem where all the spectroscopic data are given. Now look to the mass spectral data. First, look to the MPhil. This we call MPhil, the parent peak or MPhil. The molecular ion peak is 114 and its exact value is 114.1043. And I may try to reiterate that if the M peak data, the molecular mass is given with such a precision, with at least correct up to 3 places of decimal at least, then this molecular mass will represent a unique formula. There cannot be a second formula having this exact molecular mass, MPhil. And nowadays in mass spectrometer, we can get the mass MPhil data with exact precision up to several places of decimal after decimal. And we have the data from the table from which we will tally which one best suits to this molecular mass. This only takes into account carbon, nitrogen, oxygen, and hydrogen. If you have a bromine, chlorine, sulfur, which have an appreciable percentage of the M+2 peak, chlorine in the ratio 3:1, bromine 1:1, of course, sulfur is a bit less, is 4.4% is the M+2 peak, 34 peak, compared to 96.4% or 6%. So here the M+2 peak is almost undetectable. The M peak suggests that there is no bromine, no chlorine, no sulfur. Otherwise, the M+2 peak is almost undetectable. There must be M+2 peak, but here the data, the spectral data doesn't show any peak. Now, let us take into account the mass spectral data, and this I have borrowed from the great Silverstein book, the appendix. In the mass number 114, there are so many formula having mass number 114, but the exact molecular mass taking the most abundant isotopes into account will be precisely this unique. No two formula can have the exact identical molecular mass, isotopic molecular mass. Now it best suits to this one, 1043, this is 1045, and all other are far away. But one thing I must remind you, that nitrogen rule is the guiding force sometimes. And I remind you that if a molecular mass number is odd, it may contain one or odd number of nitrogen atoms. And if it is even like the case here, it will not contain any nitrogen, or if at all, there will be even number of nitrogen atoms. Usually no nitrogen atom. So here, looking to this even value mass number, we are sure, almost sure, that there is no nitrogen atom. Now, one thing I may also tell you, that if you find a mass number is even and you say there is no nitrogen, there can be nitrogen. Even a mass number is odd, but there cannot be any nitrogen, no nitrogen. So in such a case, you don't be surprised. It is due to the fact that that formula is not the formula for a neutral molecule. It is due to a radical, a monovalent radical or a bivalent radical. So that can have nitrogen, odd number of nitrogen having even mass number, or even number of nitrogen or no nitrogen having odd mass number. So don't be surprised. Nitrogen rule should be used with caution. You understand? So since this is a neutral molecule, we have not removed any monovalent group like bromine, chlorine. So we are sure that this contains either no nitrogen or even number of nitrogen. So, but it should match closely to the molecular ion, an exact molecular mass. So our choice of molecular formula is now made correctly, C7H14O. In the next video, I shall discuss how you will find out the molecular formula, not from this table, not from the precise molecular ion data, but from the M+1, M+2 and other isotopic peaks. That also will give you a very elegant method to find out the molecular formula. This table is not required. But nowadays, isotopic peaks are not used. This precise molecular mass MPic value along with the table matching is used. Now let's proceed. Now when the molecular formula is this, let us immediately find out the double bond equivalent. Now from the formula, you are almost sure that it is a formula of aldehyde or a ketone. CnH2nO. It can be an enol, no doubt, or in ether, but usually aldehyde and ketone. Let's see. Let's suspect. What is the harm in suspecting things? Now, immediately you go for double bond equivalent. C minus hydrogen by 2 minus halogen by 2 plus nitrogen by 2 plus 1. And we get there is no halogen, no nitrogen, so we get 1. So that 1 could be a carbonyl group. And the base peak, as you find here in the NMR, mass data, the base peak at 71 and equally intense peak at 43, that will be discussed at the end from the fragmentation pattern. Now we go to this data. Immediately after knowing the formula and suspecting it to be a ketone, we look to be or aldehyde, we look to the IR. IR indicates a strong intense peak at 1712, indicating it is containing a carbonyl group, and no peak at 2720. I tell you that a peak at 2720 or 30 or 40, that along with this, from the IR itself, you are confirming the presence of aldehyde. That is the aldehyde CH stretching. 2820, that might be a little confusing because that comes along with the aliphatic CH3 doublet peak, 2900 something and 2800 something. So that might be a little obscured, but 2720 30 peak is a characteristic peak for aldehyde CH stretching, right? So we are now, our suspicion grows a little more intense that it could be a ketone. No, there is no indication of an aldehyde group here. So this 2962, 2877 talks about aliphatic CH3, sp3 CH stretching. There is no aromatic CH or alkene CH, sp2 CH that would have crossed 3000 centimeter inverse. So these two are routine indicators of aliphatic CH without any carbon-carbon double bond, CH, or aromatic CH. Now, after having confirming that it might be a ketone, we look to the proton NMR peak. It gives only 3 beautiful multiplets. This is a triplet. This is a sextet 1, 2, 3, 4, 5, 6 with the usual multiplicity ratio from the Pascal's triangle. And then this is a triplet. And they are farther apart from each other. This is about 0.9 ppm. This is about 1.6. This is about 2.4 or 2.35. So this triplet and this sextet, this triplet, does it indicate you something? Is it not telling about an N-propyl group? N-propyl, an N-propyl group. So this methyl is a triplet. And this methylene is a sextet, 3 plus 2 plus 1 sextet. And this methylene is also a triplet. And you can also look to the integral peaks. The integral peaks indicates if this is 3, this is 2, this is 2. You can also have a good guess that if this is 3, this is 2, this is 2 in the ratio 3 is to 2 is to 2. So this one is the middle CH2 of the N-propyl group. This is the terminal methyl. This is a triplet. And this is a sextet. And this is also the downfield peak. Maybe that is close to the carbonyl group. It is a downfield, relatively downfield triplet for the methylene group. Now we are almost sure that since we have 3 proton peaks and the formula is C7H14O and there is a carbonyl group, a ketone, then it must be a symmetrical compound. It must be a symmetrical compound because there are only 3 proton peaks. So it could be a repetition of N-propyl on both the sides. It may be di-N-propyl ketone. Let's try to also confirm from the carbon 13 NMR. So this bottom one, the bottom one is a proton decoupled carbon 13 NMR. This peak, triplet peak at 77 is due to this solvent CdCl3. Just ignore this peak. This is a very, very characteristic peak for solvent CdCl3. And then you find there are only 4 carbon peaks. So there are only 4 types of non-equivalent carbon. And this downfield peak at about 212 is undoubtedly a carbonyl carbon, aldehyde or a ketone. It cannot be an aldehyde. Had it been aldehyde, there should have been also a very prominent peak, proton NMR peak at about 10 ppm. The downfield peak at 10 ppm, at about 10 ppm is missing out here. 2720 peak is missing out here. So there cannot be an aldehyde. It is a ketone. All right. So coming to, these 3 peaks, one is the methyl carbon, the other one is the middle methylene carbon, and this one is the desilted methylene carbon, which is close to carbonyl group, being little more desilted, right? And this is the carbonyl quaternary carbon. If you are not acquainted with C13 NMR, don't worry at all. You'll be knowing in your programs in your respective universities and colleges. And once you know, you can understand fully well. And let me tell you that DPT experiments are very cool. DEPT-135, that indicates how many methylene groups are there. The same C13, you will not find any quaternary carbon in any of the DEPT. In DEPT-135, you get the methyl and methine as a positive signal upwards, and methylene CH2 a downward signal, a negative signal. So two negative signals indicate there are two non-equivalent methylene groups, these two. Obviously, this is the middle methylene of the propyl and propyl group, and this is the other terminal CH2 connected to carbonyl group, that downfilled CH2. So that is indicated from DEPT-135. And one, the positive signals in the DEPT-135 degree is due to both methyl and methene. Methyl and methine, CH3 and CH peaks are positive signals. There is only one positive signal, but we have to confirm with the DEPT-90. DEPT-90 will only show you positive methine CH signals. There is nothing, no peak in the DEPT-90. So this is undoubtedly the methyl CH3. So there is one methyl, two methylene. I hope you remember that DEPT-135 gives you positive CH3 and CH and negative CH2. But DEPT-90 only gives methine CH positive. There is no peak. So this has to be methyl CH3. And the quaternary carbonyl peaks, they are not found in either DEPT-135 nor neither DEPT-135 nor DEPT-90. So we are almost sure that the compound is di-N-propyl ketone. So we have written all these things in proton NMR delta 0.9, 1.58, 2.37 in the ratio 3:2:2, revealed from the integral peak heights. One CH3 group and two CH2 groups are indicated, and that too should be a N-propyl group, explaining the multiplicity sextate, triplet and triplet. And the downfield peak, the uphill peak 3H 0.9 ppm is for CH3, and the middle one is 1.58. The downfield is 2.37, and the formula is so high double number of carbon atoms, excluding the carbonyl carbon. So there must be a repetition of the same group, so that there must be a 2N-propyl group with two sets of equivalent protons, two pairs of equivalent CH2 groups and one pair of, because these two methyl groups are equivalent, these two methylene groups are equivalent, these two methylene groups are equivalent. So they will give you 1, 1, 1, 3 peaks, 3 proton peaks and 3 carbon peaks for this, and 1 quaternary carbon peak for this carbonyl carbon. So we have already explained the DEPT-135 and also the carbon 13 NMR, 1D, one-dimensional carbon 13 NMR, delta 13 ppm is for methyl carbon, 17 for the middle CH2, and 45 for the most desilted methylene carbon. Methylene carbon bonded to the carbonyl group, and the carbonyl group has a mass desilted 212 ppm. And this 77 peak is to be ignored. And the mass spectral fragmentation pattern we have done, this is the alpha cleavage with one electron shift. The loss of N-propyl radical will give you this resonance stabilized positive ion is M/E71 is the best peak. And two electron shift Removing this as radical and N-propyl carbocation M by E43 is equally prominent in tense peak. But very interestingly here, the McLaportive peak is very, very weak. We cannot say the reason why it is weak in this case. 58 peak should be very strong, but in this case, we don't find a strong McLaportive peak. That depends on the reaction condition, the measurement condition. So the loss of ethylene with a gamma hydrogen transfer, the McLaportive rearrangement would have given a strong, I'm sorry, 86, not 58. The 86 peak is very, 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 very weak. So that is a surprise for all of us because ketones having gamma hydrogen are very susceptible for the McLaportive rearrangement. So this ends our problem number 1. Let us go to the problem number 2, that is 4.4c. Let's look through. This will be a little easier on our part because we have already discussed the methodology, how to proceed. Now look here, in the mass spectral data, you find both M peak and M plus 2 peak. 170, whose actual value, oh, not this one. This is not the data. So this is the M peak. This one, the exact M peak data is 169.9735. And but the mass number is 170, and this is M plus 2 peak. This is M plus 2, and this is M. So they are almost of equal abundance, 1:1 ratio. So if M and M plus 2 peak comes in the ratio 1:1, then you are sure that there is one bromine atom. Right? Slowly and steadily, we will be taking up many problems where we will be discussing all the details. Not that everything will be taken up in a particular problem. So don't worry. Keep on watching my videos. You'll be getting a lot of information where I will be trying to disseminate my experience. So M plus 2 peak and M peak is 1:1. So there is one bromine atom. So now let us try to subtract the isotopic mass of the most abundant isotope, equally abundant isotope, that is of having lower molecular mass, isotopic mass 79, and the exact isotopic mass of the 79 isotope is 78.9183. You have to also borrow this data from some good source like Silverstein. I have borrowed. Now from the mass MPIC data, exact data, I subtracted the isotopic mass of 79 isotope, this one, and I got the remainder 91.0552. Now I took up the appendix data. I find in the 91, mass number 91, these are the only possibilities. And don't be surprised that 91 is odd, that it must contain a nitrogen. No, it may not, because we have removed a monovalent bromine atom. So this 91 is not a neutral molecule. It is a part of the molecule and a radical. Therefore, it can be odd but carry no nitrogen. But the best match has to be found out. 0552, this is 0508. So this is 0548, which is very close to 0.0552. So the best match comes from here. And suspicion of not having nitrogen is already there because we have already subtracted a monovalent bromine atom. So this is not a full molecule, it's a part of the molecule. So it can be odd. So this is our best choice. C7H7 is the part formula. So the part formula from the part molecular mass, this one is this one, and bromine to be added. So the molecular formula now becomes C7H7Br. Now the DBE double bond equivalent is 7 minus 7 by 2 minus halogen is there. 1 by minus 1 by 2 plus 1 comes 4. When you get a DBE double bond equivalent or index of hydrogen deficiency as 4, you can suspect the compound to be aromatic because the benzene ring itself has a DBE of 4, 3 for the 3 double bonds and 1 for the ring. So you suspect immediately, then look for the corroborative data from the proton NMR, from IR, and also from carbon 13 NMR. Now, the presence of benzene ring is immediately known from the data. I show you the data here. The proton NMR peak has two prominent peaks in between 7 to 8. So this is the reason 6.5 to 8.5 is the reason for aromatic CH. And also 110 to 150, 60 are the, the reasons for the aromatic carbon atoms. So we get carbon resonances in the C13 NMR and also the proton NMR between 7 to 8. So aromatic benzene ring is confirmed. Now, since the formula is C7 and benzene is C6, there will be only one carbon left out. That could be a methyl group because there is no more unsaturation. The unsaturation is already satiated with benzene 4, but we have one carbon more. So that could be methyl, and bromine is another substituent. So the benzene ring is disubstituted. That is known from the 2 proton peaks in the aromatic region. Now, let me show you, had it been, if it is, supposing tentatively, we give the formula this of our unknown compound. So these two ortho to methyl, they are equivalent, and ortho to bromine, they are also equivalent. This is close to electron withdrawing group, EWG. So this will be X and this will be A. We will not discuss in details. This will be not a A2X2 system. It is a AA-XX- system because the two are not magnetically equivalent, although they are shift equivalent. So such a spectra, AA-XX- system, is really a non-fast order spectrum. And often we get non-fast order nature, but we are ignoring those little peaks in the sides, and we are not taking the expansion. We are taking viewing it from a distance without entering into the complexity of the pattern. We are looking a apparent doublet for each. So I'm sorry, this is H. This is HX. Now only the J3 coupling is to be considered. So this A peak is a doublet due to J3 coupling. These J3, J4 and J5, they have been ignored. They have been just sidetracked. Similarly for X, only the J3 coupling is taken. So it is an apparent doublet. It should be a double doublet or doublet of doublet of doublet because there is a meta coupling, there is a para coupling. So we'll not go into the details of it. We will say it is an apparent doublet and this is an apparent doublet. This is for the X dash and this is for A dash. So had it not been para, had it been ortho or meta, we would have all the 4 CH protons to be non-equivalent, would have got 4 CH peaks. And if you say that CH peaks can be very close and they can give a overlapping complex multiplet in proton NMR. You can verify that. You can get rid of those confusion from carbon 13 NMR. It would give 4 CH carbon picks. That would be also supported by the DEPT-90 to give you 4 CH picks. Let's now look to DEPT. C13 NMR in the aromatic region shows only 4. The little dwarf peaks, they are for the quaternary carbon connected to no hydrogen. That means for the disubstituted compound, that carbon, which is quaternary. And these two tall peaks, they are CH. How to know it is CH? In the DPT, this is DPT-135. In DPT-135 degree, you find one positive peak here, and the corresponding DPT-90 is absent. So this is bound to be a methyl, because methine CH gives a peak in the DPT-90. So this one is a methyl. And in DPT-135, you get the information of CH3, CH2, no negative peak, means there is no CH2, and methine, CH. So these two are methine that can be corroborated by its presence in the DEPT-90. So these two CH peaks are confirmed. This is methyl and this is 2-methine. And we have only 4 peaks. This is for the quaternary carbon. This is for the quaternary carbon. Had it been ortho or meta, you would have got 4 CH peaks, because in para, these two carbons are equivalent, giving you 1 peak, this one. And the downfield, this one, the first one among the two which are very close. And these two are also equivalent. Therefore, they give 1 peak. So only 2 CH peaks will be found. But had it been ortho, just I am showing you ortho, same thing can be applicable. Had it been this, then this CH proton carbon, this CH proton and also carbon, this CH proton as well as carbon, this proton as well as carbon, they would be different, non-equivalent. Yes, there might be possibilities of overlapping in proton NMR, but the carbon NMR will be distinct and it will be supported by 4 positive signals in the DEPT-90. That is not there. So it is 101% para disubstituted compound. One of the groups is methyl, the other one is bromine. There is no doubt about it. Let us now read out. We have seen all these doublets. This is apparent doublets are for the 2AA dash and XX dash, and this is singlet for this methyl, which has no neighboring proton. It's not split. So this is 3 proton singlet, 3:2:2. You can also have a guess on the integral heights. This is 3, this is 2, this is 2. You can also measure with a scale if you are little suspicious about their ratios, 3:2:2. So everything is now crystal clear. So we get the IR data. There is a peak at 3032, indicating aromatic CH. This methyl 3032, this one. These two are aliphatic, sp3CH, that is for the methyl doublet, below 3000 centimeter inverse, and above 3000 centimeter inverse is for the aromatic, or it is ethylenic, vinylic, but there is no C double bond C data. Had it been a double bond, then there would be a proton NMR data between 4 to 6. So there is no proton NMR from 4 to 6. So a vinylic proton is absolutely not a possibility, only aromatic CH. So everything now fits in and gives the structure to be para bromotoluene, or more correctly, 1-bromo-4-methyl-benzene. So I have already told you deep depth 135 suggests one CH3 group in the uphill region. Depth 90 suggests two methine groups in the aromatic region. So the symmetrical para-disubstitution is confirmed. Had it been ortho or meta, all the four aromatic CH protons would have been non-equivalent. Also, four CH carbons would have been non-equivalent and would have got four carbon peaks indicated, would have been indicated, would have been formed in the depth 90. But we have only two CH carbon peaks, the tall ones. The dwarf ones are for the quaternary carbons. These two. Where is it? These two. These are the quaternary, no proton attached to this carbon, right? So we come to the close, and the interesting point here is the tropylium ion peak in the mass spectral data. You get an intense peak at 91. 91 means a tropylium ion, and 65 is its sister, the loss of acetylene. Interestingly, loss of bromine also can give you 91 peak. From the molecular mass, what is given 170 or something like that, 170. If you subtract 79, then you will get the same 91. It could be due to the loss of bromine, but the further loss of acetylene to give you a M/E 65 peak, a 5-membered ring, a stable course, it is anti-aromatic. Even then, this 65 peak is indicative of the presence of tropylium ion, because the loss of only bromine, this one, it is very hard to understand how a acetylene will be removed and we get a 4-membered ring. So that is little. 4-membered rings are very unstable. So we can think that some complex hydrogen transfer rearrangement is happening, so that when this hydrogen is going for the beta cleavage to giving you the tropylium ion, that hydrogen is coming here with a simultaneous loss of bromine. So you might be having a tropylium ion. That is my gut saying, but you can as well say loss of bromine and loss of acetylene to give you base peak 91 and 65. So we come to the close of the conjoint problems from Silverstein, and there are two problems we have taken from 4.4. A, C, B we have just reserved for a future exercise. So tell me, how did you like it? And if you have liked it and you are following, why not you have, thumbs up, make a thumbs up, like in my channel. And also, if you have not subscribed, why not you do not subscribe? Please subscribe to my channel to encourage me to go for more and more such videos for you. Bye-bye.